Tonight, we're going to talk about a machine that has been drifting through space for nearly 5 decades and still hasn't stopped working. Voyager 1. It's now billions of miles beyond the outer edge of our solar system, further from Earth than any human-made object has ever traveled. The temperature out there hovers just a few degrees above the coldest temperature the universe allows. There's no sunlight to warm it, no atmosphere to insulate it, nothing but the deep, dark, frozen void between the stars. And yet, against every reasonable expectation, Voyager 1 is still functioning, still sending signals back across billions of miles. By the end of tonight, you're going to understand exactly how this machine has stayed warm and alive for nearly 50 years in one of the most hostile environments the universe has to offer. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Voyager 1 wasn't built to last this long. It launched on September 5th, 1977, riding a rare alignment of the outer planets that let a single spacecraft visit Jupiter and Saturn using gravity assists, slingshotting from one to the next. The mission plan was simple: fly past Jupiter, study its moons and its great red spot, use Jupiter's gravity to reach Saturn, study its rings and its largest moon, Titan, report everything it found back to Earth. Then the mission would be over. That was the plan. But Voyager 1 didn't stop after Saturn. The instruments kept measuring, the transmitter kept sending, the computers kept running. Decade after decade, the engineers watching the data come back from increasing distances realized they had something on their hands that nobody had designed for. A machine that simply would not quit. To understand why that's remarkable, you need to understand what the environment of deep space actually does to machines over decades. Most people, when they think about the dangers of space, focus on the launch, the roaring engines and the violent acceleration, the acoustic shockwaves that can shake a spacecraft apart if the structure isn't designed to handle them, the thermal stress of the engines running at extreme temperatures. These are genuine challenges, and they're ferocious ones. But they are also brief. The launch lasts minutes. What comes after lasts decades. And what space does to hardware over decades is where the real, less celebrated story begins. The first thing space does is remove the air. This seems obvious, but the implications cascade in ways that aren't immediately intuitive. On Earth, air is involved in almost every aspect of how heat moves. When something gets too hot, we blow air on it. When a car engine runs hot, coolant circulates through a radiator and air flows across the radiator fins, carrying heat away. When you step outside in winter, the wind steals warmth from your skin through convection. Every cooling system we've ever built for anything, from the fan in a computer to the cooling system in a nuclear power plant, relies on a fluid medium to carry heat from where it is generated to where it can be released. In space, there is no fluid medium. There is no air to convect heat. There is no water to carry it. The only mechanism left for heat transfer in vacuum is radiation. All objects above absolute zero radiate electromagnetic energy continuously. The hotter the object, the more energy it radiates, and the shorter the characteristic wavelengths of that radiation. Very hot objects radiate visible light. Moderately warm objects radiate in the infrared. Very cold objects radiate in the far infrared and microwave ranges. But every object above absolute zero radiates something. This is called thermal radiation, and in space, it is the only way a spacecraft can lose heat to its surroundings, and the only way the surroundings can transfer heat to the spacecraft. The rate at which an object radiates energy depends on its temperature. As an object cools, it radiates less energy per second. This means cooling in a vacuum is a self-limiting process. The colder the object gets, the slower it cools. This has a practical consequence. Objects floating in deep space cool far more slowly than intuition suggests. The popular image of something instantly freezing solid in space is physics fiction. The reality is a slow, gradual decline. The background temperature of interstellar space is set by the cosmic microwave background. This is the radiation left over from the early universe, the thermal afterglow of the epoch when the cosmos cooled enough for electrons and protons to combine into atoms, and photons were free to travel for the first time. That occurred about 380,000 years after the beginning of everything. The radiation produced then has been traveling through space ever since, stretching as the universe has expanded. Today, it fills all of space uniformly in every direction, and its temperature corresponds to about 2.7 degrees above absolute zero. Absolute zero is minus 459.7 degrees Fahrenheit, or minus 273.15 degrees Celsius. The cosmic microwave background temperature is about minus 454.7 degrees Fahrenheit, or minus 270.45 degrees Celsius. That is 5 degrees warmer than absolute zero. Absolute zero is the theoretical floor, the temperature at which all classical molecular motion stops. At that point, there is no kinetic energy left to extract. Nothing can be colder. Interstellar space sits within 5 degrees of that floor. For almost every purpose you can think of, interstellar space is as cold as things get, and Voyager 1 is moving through that environment right now. The spacecraft is not instantly freezing because of the thermal physics described above. It radiates slowly, and it carries its own internal heat source. But make no mistake about the ambient condition. If you removed the power source and the insulation, the spacecraft would slowly cool toward that 2.7 degree baseline. The fact that it has not, after nearly 5 decades, is the direct result of the engineering choices made by people in the 1970s. The heat source that has kept Voyager 1 alive is called a radioisotope thermoelectric generator. The acronym is RTG. Engineers and physicists have used that abbreviation long enough that most of them probably never say the full name anymore. But the full name is worth parsing carefully because each word describes exactly what the device does. Radioisotope. A radioactive element whose atomic nuclei undergo spontaneous decay, releasing energy in the process. Thermoelectric. A device that converts thermal energy directly into electrical energy without moving parts, using a physical phenomenon called the Seebeck effect. Generator. The device generates electrical power. Put them together. A device that converts the heat from radioactive decay into electrical power. The Seebeck effect, which the thermoelectric part of the name refers to, is worth a brief explanation. In 1821, the physicist Thomas Johann Seebeck discovered that if you create a temperature difference across a junction between two different electrical conductors, a voltage develops across that junction. The larger the temperature difference, the larger the voltage. This is the Seebeck effect. In an RTG, the radioactive material on one side of the thermoelectric junction is hot because of nuclear decay. The other side faces space and is cold because it radiates heat away. The temperature difference drives a voltage. The voltage drives a current. Electrical power flows. No moving parts. No combustion. No fuel to feed. No pumps to maintain. Just atoms decaying on one side and cold space on the other. The elegant brutality of physics doing exactly what it does, whether anyone is watching or not. The specific radioactive material in Voyager 1's RTGs is plutonium-238. This is not the same isotope used in nuclear weapons, and the distinction matters. Nuclear weapons use plutonium-239. Plutonium-238 is a different configuration of the nucleus, with a different number of neutrons, and it has completely different properties. Plutonium-239 can undergo fission in a chain reaction, releasing enormous amounts of energy very quickly. This is what makes it useful in weapons, and also what makes it unsuitable as an RTG fuel. You don't want your power source chain reacting. Plutonium-238 decays through alpha emission. An alpha particle is a helium nucleus, 2 protons and 2 neutrons bound together. When a plutonium-238 nucleus ejects an alpha particle, it transforms into uranium-234 and releases energy. That energy becomes heat. Alpha particles are relatively easy to shield against. A thin layer of material, even an inch or two of most solids, stops alpha particles entirely. This makes handling plutonium-238 safer than many other radioactive materials used in similar contexts. The half-life of plutonium-238 is 87.7 years. This is the critical number. Half-life is the time for exactly half of a given quantity of radioactive material to decay. After 87.7 years, half remains. After 175.4 years, a quarter remains, and so on. The 87.7-year half-life was chosen deliberately. It is long enough that the RTGs still produce useful power decades after launch. If the half-life were 10 years, the power would be nearly exhausted after 50 years. If the half-life were 1,000 years, the decay would be so slow that the heat output would be too low to be practically useful. 87.7 years is in the sweet spot for missions expected to last years to decades. At launch in September of 1977, Voyager 1's 3 RTGs together produced approximately 470 watts of electrical power. That is not a lot. A modern laptop computer uses roughly 40 to 100 watts. A standard electric space heater uses 1,000 to 1,500 watts. 470 watts is less than most hair dryers use on high heat. But in the context of Voyager 1, it was more than enough. The spacecraft was designed to use that power efficiently. Every instrument, every computer, every heater, every system was designed to operate within that budget. And because the budget was known in advance, the design could be optimized around it. As of the mid-2020s, nearly 50 years after launch, the RTGs produce somewhere between 200 and 250 watts of electrical power. The output has declined for 2 reasons. First, the plutonium-238 is decaying into uranium-234. After nearly 50 years, which is more than half of one half-life, the original quantity has decreased to about 70% of the launch amount. Less plutonium means less heat. Second, the thermocouples that convert heat into electricity have degraded. They accumulate radiation damage over decades. The materials change slightly. The Seebeck coefficient, which determines how efficiently a temperature difference is converted to voltage, decreases over time. This degradation is harder to predict precisely than the radioactive decay, but both effects have been tracked carefully throughout the mission. Despite the decline, the RTGs still produce power, and they will continue to produce power for years. Not because anyone is doing anything to maintain them, not because there is a crew aboard monitoring them, but because the physics of radioactive decay does not need anyone to tend it. It just happens, reliably, on schedule, indifferent to the cold, indifferent to the dark, indifferent to the distance from Earth. Atoms decay according to quantum mechanical probability, and quantum mechanics does not care about the convenience of engineers. That indifference is, paradoxically, the most reliable thing about the RTG. The thermal management of Voyager 1 is more complex than most descriptions acknowledge. And the complexity matters for understanding both why the spacecraft is still alive and how close to the edge it has been operating for years. Different parts of the spacecraft have different temperature requirements. Electronics have a minimum operating temperature below which their electrical properties shift outside acceptable bounds. Mechanical systems have minimum temperatures below which lubricants freeze or materials become too brittle. Propellant systems have minimum temperatures below which the propellant itself freezes. All of these constraints have to be satisfied simultaneously, using heat that is a declining resource. The spacecraft's insulation is the first line of defense. The thermal blankets wrapped around the spacecraft body are multi-layer insulation assemblies. They consist of multiple layers of thin, reflective film, typically aluminized polyester film of the type commercially known as mylar, separated by mesh spacers. The outer layers reflect incoming radiation. The inner layers trap heat generated by the RTGs and the electronics. The mesh spacers create vacuum gaps between the layers, suppressing heat transfer by conduction. The result is insulation that is highly effective at preventing heat loss through radiation. The thermal blankets work because they create many successive barriers, each of which reflects a fraction of the outgoing radiation. The more layers, the more effective the insulation. Voyager 1's thermal blankets were designed with specific layer counts to achieve specific insulation performance targets. Those targets were chosen conservatively. The engineers knew that they couldn't predict with certainty how the thermal environment would evolve over decades, so they built in extra layers, extra margin, more insulation than the nominal design required. That conservatism has paid dividends for nearly 50 years. Inside the thermal blankets, the waste heat from the electronics and the residual heat from the RTGs maintain the interior of the spacecraft body at temperatures compatible with operation. As power has declined over the decades, the interior has cooled somewhat. But because of the thermal blankets, the rate of cooling has been gradual and the temperatures have remained above critical thresholds. For most of the spacecraft body, not all of it, some external components, instruments mounted on booms away from the main body, propellant lines, and thruster assemblies, have had their own thermal management challenges. These are the components that have required the most active management as power has declined. They are the places where the margin has been tightest. They are the places where the decisions made over the years have been the hardest. The hydrazine propellant system deserves extended attention because it is, in a sense, the most fragile critical system on the spacecraft. Hydrazine is a liquid under normal conditions. It's used extensively in spacecraft propulsion because it can be stored as a liquid for long periods. It reacts catalytically without needing an oxidizer or an ignition system, and it produces a reasonably high exhaust velocity. Small hydrazine thrusters are standard equipment for attitude control on many spacecraft. The problem with hydrazine in a thermal context is its freezing point. Hydrazine freezes at 1.4 degrees Celsius, which is 34.5 degrees Fahrenheit, just barely above the freezing point of water. That temperature might seem tolerably mild, but consider the environment. Voyager 1 is in interstellar space at a background temperature of 2.7 degrees above absolute zero. The spacecraft has almost no external heat input. Any part of the propellant system, not actively heated, would cool toward the ambient temperature of the interstellar medium over time. Without heaters on the propellant lines and thruster assemblies, the hydrazine would freeze. And if the hydrazine freezes, the thrusters cannot fire. And if the thrusters cannot fire, the spacecraft cannot adjust its orientation. And if it cannot adjust its orientation, the high-gain antenna will drift away from Earth. And when that happens, communication is lost permanently. That's the chain. For most of the mission, dedicated electric heaters prevented this. But electric heaters require power. As the RTG output declined year by year, maintaining every heater became increasingly expensive in terms of the power budget. So the team faced a slow, recurring dilemma. Every heater they could turn off freed up power to keep the spacecraft talking for longer. But every heater they turned off brought some part of the spacecraft closer to a temperature where something could fail, and in the case of the propellant lines, closer to the point where the hydrazine could freeze. By the mid-2010s, the propellant line temperatures had become a genuine concern. The margins above the freezing point were thinning as the spacecraft cooled. The team had to build new thermal models, decades after launch, just to understand how cold different parts of the spacecraft were getting. Because the original engineers never expected anyone to be managing these margins half a century later. Each decision became a careful trade-off. Keep a heater on and burn power that might be needed elsewhere. Turn it off and accept a little more risk that something critical gets too cold. So far, through careful management, the hydrazine has stayed liquid and the propulsion system has stayed operational. And Voyager 1 has kept talking. This kind of decision exemplifies the management that has characterized the mission for decades. Not dramatic engineering breakthroughs. Not revolutionary discoveries. Just careful, conservative, informed decision-making by people who understood their spacecraft deeply and trusted their models carefully. That's how you keep something alive for 50 years in a place where nothing should survive. The communication link between Voyager 1 and Earth is perhaps the second most extraordinary technical achievement of the mission, after the simple fact that it still exists. Voyager 1's transmitter operates at a frequency of about 8.4 gigahertz, which is in the X-band portion of the radio spectrum. At X-band frequencies, the antenna can focus the transmitted energy into a relatively narrow beam. A narrow beam means more of the transmitted power actually reaches the target, rather than spreading off in useless directions. The spacecraft's high-gain antenna is a parabolic dish about 12 feet in diameter. The parabolic shape reflects transmitted radio waves into a tightly focused beam. The same dish shape catches incoming signals and focuses them onto a receiver. The transmitter that feeds this antenna produces about 22 watts of radio frequency power. A standard light bulb is 40 to 100 watts. Voyager 1's radio transmitter, the device that sends signals across tens of billions of miles, is less powerful than a dim household light bulb. By the time that signal arrives at Earth, it has expanded into a sphere of radiation with a radius of roughly 16 billion miles. The fraction of the transmitted power that arrives at any given antenna on Earth is correspondingly tiny. The signal strength received at Earth is something in the range of 10 to the negative 17 watts. Numbers that small are genuinely difficult to work with conceptually. The point is that what arrives at Earth is almost vanishingly faint. Extracting a useful signal from that requires technology that pushes the limits of what we know how to build. The Deep Space Network is the answer to this problem. It's an international network of large radio antenna complexes maintained by NASA and operated by the Jet Propulsion Laboratory. 3 primary sites are located around Earth, one at Goldstone in the Mojave Desert in California, one near Madrid in Spain, and one near Canberra in Australia. The 3 sites are spaced roughly evenly around Earth's circumference. This geographic distribution ensures that at any given moment, as Earth rotates, at least one site has Voyager 1 above its horizon and can maintain contact. The individual antenna dishes at these sites are enormous. The largest are about 230 feet in diameter. Even with dishes that size, extracting Voyager 1's signal from the background noise of the universe requires sophisticated signal processing. Radio astronomers describe it as finding a whisper in a stadium. The universe is full of radio noise, from other stars, from energetic phenomena like pulsars and quasars, from the cosmic microwave background itself. Voyager 1's signal is buried in all of that. Pulling it out requires knowing exactly where to look, at exactly what frequency, and applying processing algorithms specifically designed to extract the coherent signal from the incoherent noise. The fact that it works every day, that engineers can sit at computers in California and receive data from a machine nearly 50 years into its journey, is not a given. It is an achievement that requires active effort and sophisticated technology on both ends. The network itself has been upgraded multiple times during the mission. Computers have been replaced. Processing algorithms have been improved. In some cases, the ground system's ability to receive Voyager 1's data has actually improved since launch. Even as the spacecraft's transmitter has remained the same and the distance has increased. The spacecraft on one end, the ground network on the other, both contributing to a communication link that spans a distance that no previous technology had ever attempted. Voyager 1's encounter with Jupiter in March of 1979 produced results that surprised even the scientists who designed the mission. The spacecraft made its closest approach to Jupiter at a distance of about 172,000 miles from the planet's cloud tops. It was close enough that the radiation environment around Jupiter was intense enough to cause concerns about instrument damage. Jupiter has a powerful magnetic field, about 20,000 times stronger than Earth's. That field traps energetic charged particles in radiation belts similar to Earth's Van Allen belts, but far more intense. Mission planners had designed Voyager 1's trajectory to minimize exposure, but some exposure was unavoidable. The spacecraft survived the encounter with its instruments intact. What it found was transformative. The Great Red Spot observed through telescopes since the 17th century, was revealed in close-up detail for the first time. It is a hurricane-like anticyclone in Jupiter's atmosphere, rotating counterclockwise over a period of about 6 days. Its inner structure showed swirling cloud bands and complex vortex dynamics that no telescope observation could have revealed. But the bigger surprise was Io, Jupiter's innermost large moon. Voyager 1 discovered that Io is the most volcanically active body in the solar system. Before the flyby, Io was expected to be a geologically dead world, a frozen body, like many other moons. Instead, the cameras found active volcanoes in eruption. Plumes of sulfur compounds rising hundreds of miles above the surface. Flows of molten material, coloring the landscape in yellows and oranges and reds. A surface so actively reshaped by volcanic activity that it shows almost no impact craters, because new eruptions constantly resurface and bury any craters that form. What makes the discovery remarkable is the timing. Just 3 days before Voyager 1 reached Jupiter, a team of researchers published a paper predicting that Io might be heated internally by tidal forces, the constant gravitational kneading caused by Jupiter and the other large moons. They suggested the spacecraft might see the surface consequences. 3 days later, Voyager 1 did exactly that. It is one of the cleanest examples in the history of planetary science of a bold prediction confirmed almost immediately by direct observation. That's how science is supposed to work. Europa, Jupiter's second large moon, showed a surface of bright water ice crisscrossed by dark lines. The lines were identified as cracks in the icy crust. The relatively smooth surface suggested that the ice was floating on something, possibly a liquid water ocean beneath the ice. That inference, first seriously raised as a possibility by Voyager 1 data, has since been confirmed by subsequent missions. Europa has a subsurface liquid water ocean. It may be one of the most promising places in the solar system to search for extraterrestrial life. That idea started with Voyager 1. The Saturn encounter in November of 1980 was in some ways even more revealing. Saturn's ring system, visible through telescopes as a broad, smooth disk, turned out to be vastly more complex than anyone had expected. The cameras on Voyager 1 resolved the rings into thousands of individual ringlets. Some ringlets were not smooth. They showed a braided structure, multiple strands twisted around each other. Others showed gaps and density variations that couldn't be explained by simple gravitational dynamics. The rings turned out to contain structures at every scale, a complexity that has kept ring scientists busy for decades. The moon Titan received special attention because it was scientifically unique. Titan is the only moon in the solar system with a dense atmosphere. The atmosphere is primarily nitrogen, similar to Earth's atmosphere in broad composition, but also contains methane and complex organic molecules. The instruments on Voyager 1 found a chemical complexity in Titan's atmosphere that suggested it might be somewhat analogous to the early Earth atmosphere before life emerged. Titan's surface was hidden behind a thick orange haze of organic aerosols. Voyager 1 couldn't image the surface directly. But the atmospheric measurements showed something extraordinary, a world with weather systems, with atmospheric chemistry, with conditions that organic chemists found deeply interesting. Saturn's other moons produced their own surprises across the Voyager encounters. Enceladus showed hints of a suspiciously smooth surface in places, suggesting recent geological activity. Mimas showed a crater so large that the impact that formed it must have nearly shattered the moon. Iapetus showed the two-tone coloring that had puzzled astronomers since its discovery in the 17th century, one hemisphere far brighter than the other. Every moon was its own world. Every flyby produced new data that required new models. Voyager 1 didn't just confirm existing theories. It produced discoveries that required new theories to explain them. There is something specific about the way the 1970s engineering philosophy shaped Voyager, one that has been the source of its longevity, and it's worth understanding in some detail. In the 1970s, computer memory was expensive. Processing power was limited. Bandwidth was limited. Mass was limited. Power was limited. Every design choice involved trade-offs between competing constraints, and every trade-off had a cost. In that environment, the instinct might have been to design to the minimum. Give the spacecraft just enough of everything to complete the primary mission and no more. The pressure to minimize was real. The budget was finite. The launch window was fixed. But the team that built Voyager made a different choice in the places that mattered most. They added more thermal protection than the minimum design required. They added redundant computers. They added backup thruster sets. They designed the electronics to operate at temperatures below their nominal specifications, so that if the heaters failed or were switched off, the components would still work. They added margin. Not everywhere. There wasn't budget for margin everywhere. But in the places where failure would be catastrophic, they spent the extra mass and cost. And those decisions, made by people who had no way of knowing they were building a spacecraft that would be in service for 50 years, are the reason the spacecraft is still in service 50 years later. The redundant thrusters that were untouched for 37 years and then fired perfectly in 2017. The thermal blankets that kept the hydrazine from freezing when the heaters were switched off. The backup computer systems that allowed a corrupted chip to be routed around in 2024. All of these capabilities were built in the 1970s by engineers who expected the mission to last 5 years. They built better than they needed to. And we are still benefiting from that. In August of 2012, something happened that astronomers and mission scientists had been anticipating for years. Voyager 1 crossed the heliopause. The heliopause is the boundary where the sun's influence ends. To understand what that means, you need to understand the heliosphere first. The sun is not just a ball of light and heat sitting passively in space. It's an active object that continuously ejects material outward in all directions. The solar wind is a stream of charged particles, primarily protons and electrons, that flows outward from the sun at speeds ranging from about 250 to 500 miles per second. This wind doesn't stop at the orbit of Pluto. It doesn't stop at the edge of the Kuiper belt. It pushes outward, carrying the sun's magnetic field with it, inflating a vast bubble in the surrounding interstellar medium. That bubble is called the heliosphere. Inside the heliosphere, the solar wind dominates. The particles are primarily from the sun. The magnetic field is primarily the sun's extended field. The environment is shaped more by the sun than by anything else. Outside the heliosphere, the interstellar medium dominates. The particles come from other sources: supernova remnants, cosmic ray accelerators, the broader structure of the galaxy. The magnetic field belongs to the larger galactic structure, not to our sun. The pressure at the heliopause is a balance between the outward pressure of the solar wind and the inward pressure of the interstellar medium. Where those two pressures equalize, the boundary forms. Before Voyager 1 crossed that boundary, we had models of what it might look like, but we had never actually been there. No instrument had ever directly sampled that transition. What the instruments on Voyager 1 found was more complex than the models had predicted. The boundary wasn't a sharp line. There was an extended transition region called the heliosheath, a turbulent zone where the solar wind slowed dramatically and became dense and hot. The spacecraft crossed a shock wave called the termination shock in December of 2004, where the solar wind slowed from supersonic to subsonic speeds, at a distance of about 94 astronomical units from the Sun. It then spent years moving through the heliosheath before finally crossing the heliopause itself in August of 2012 at about 121 astronomical units. At the heliopause, the instruments recorded a dramatic change. The density of charged particles from the solar wind dropped precipitously. The density of galactic cosmic rays, particles from outside the solar system, jumped sharply. The magnetic field changed direction. These changes confirmed that the spacecraft had crossed into genuinely different territory. From one side of the heliopause to the other is the difference between our solar system's environment and the broader galaxy. Voyager 1 crossed that boundary as a functional spacecraft with working instruments, and it documented the crossing in detail. That data, the first in situ measurements of the heliopause transition, has been the subject of dozens of scientific papers and has fundamentally changed our understanding of how the heliosphere interacts with the interstellar medium. The instruments that made those measurements deserve some attention, because understanding what they measure is the difference between knowing that Voyager 1 is out there and understanding why it matters that it is. The plasma science instrument measured the properties of the solar wind throughout the inner and outer heliosphere. It tracked the density, temperature, and velocity of the charged particles surrounding the spacecraft. As Voyager 1 moved outward, this instrument watched the solar wind grow thinner and slower, documenting the gradual decline of the Sun's influence. The magnetometer tracked the direction and strength of the magnetic field surrounding the spacecraft. Inside the heliosphere, this was primarily the Sun's magnetic field, carried outward by the solar wind in the spiral pattern first predicted by astrophysicist Eugene Parker in the 1950s. Beyond the heliopause, the field it measured belongs to the broader galaxy. The cosmic ray subsystem and the low-energy charged particle instrument counted particles at different energy levels. These instruments were crucial for identifying the precise moment of heliospheric crossing because the ratio of solar particles to galactic cosmic rays changed dramatically and abruptly at the boundary. The plasma wave science instrument detected oscillations in the electron plasma of the medium surrounding the spacecraft. This instrument became particularly important in interstellar space, where it detected signals produced when solar activity sent shock waves outward through the interstellar medium, producing detectable oscillations in the electron plasma, even billions of miles from their source. In a real sense, this instrument allowed scientists to hear the interstellar medium, not literally, because sound requires a physical medium dense enough to carry pressure waves, and interstellar space is far too thin for that. But the oscillations it detected could be converted to audio frequencies, and the resulting sound was a faint, steady hiss, punctuated by changes in pitch and intensity that corresponded to changes in the density of the surrounding plasma. Scientists called it the hum of interstellar space. It is one of the stranger and more evocative data products ever produced by a spacecraft. The photopolarimeter and the infrared spectrometer and the ultraviolet spectrometer were all eventually switched off as power declined. The cameras, the imaging science subsystem, were powered down in 1990 after the famous pale blue dot photograph. But the particles and fields instruments kept running far longer, deep into interstellar space. They are the right tools for the environment. Voyager 1 now occupies a medium with no solid surfaces to photograph and no bright objects to image, but with magnetic fields and particle flows and plasma oscillations that are unique in all of human experience. In late 2023, Voyager 1 experienced what mission controllers described as the most serious anomaly of the spacecraft's operational life. The Flight Data System computer began producing corrupted output. The Flight Data System is the computer responsible for collecting science and engineering data from the spacecraft's various systems, formatting it into a transmittable data stream, and feeding it to the radio transmitter. It is, in a real sense, the voice of the spacecraft. When it works correctly, the data flowing from it tells engineers everything about the state of the vehicle, which instruments are running, what they're measuring, what temperatures the various components are at, whether any systems are showing anomalous readings. When the Flight Data System began producing garbled output in late 2023, that voice went unintelligible. The data stream, arriving at Earth, was nonsense. Not completely absent, which would have been unambiguous. Something was being transmitted. Something was arriving. But it didn't make sense. The patterns didn't correspond to expected data formats. The content was uninterpretable. This is actually a harder situation to diagnose than a complete loss of signal. With a complete loss, the problem is clearly the transmitter, or the antenna, or the communication link. With garbled data, the problem could be anywhere in the signal processing chain. The team began methodically eliminating possibilities. Each test required sending a command, waiting more than 20 hours for it to arrive and be executed, then waiting another more than 20 hours for any response. A full round of testing took more than 40 hours. This process, repeated many times over weeks and months, gradually narrowed the possibilities. Eventually, the team pinpointed the source. A single chip in the Flight Data System memory had become corrupted. Not the whole computer. Not the processor. One specific chip that held part of the memory used by the computer's firmware. The chip stored instructions that the computer executed when formatting data for transmission. With those instructions corrupted, the formatted output was garbage. Now came the real engineering challenge. The chip itself could not be replaced. The spacecraft is at the other end of a 22-hour communication delay, and nothing aboard it is designed to be serviced after launch. But the chip was only responsible for storing the corrupted code. If that code could be moved to working memory chips elsewhere in the computer could execute the code correctly and produce clean output. The challenge was that the computer had very limited available memory. 68 kilobytes in total, a number that would be considered trivially small by the standards of any modern device. Moving the corrupted code meant finding space in the remaining working memory and redistributing the existing content to make room. The code itself had to be broken into smaller pieces because no single available block of memory was large enough to hold all of it. Each piece had to be written and tested separately, and all the pieces had to work together correctly when the full system was operating. The team spent months developing and testing this approach on ground-based simulators that replicated the Voyager 1 computer architecture. They tested every scenario they could think of. They tested failure modes. They tested edge cases. They ran the new software configuration repeatedly to verify it behaved correctly. Then they sent the commands. In April of 2024, the new code ran on Voyager 1 for the first time. The data stream came back clean. Engineering telemetry arrived, readable and interpretable. Scientific data from the instruments arrived, readable and interpretable. The team had successfully rewritten the firmware of a 46-year-old spacecraft computer across a distance so great that a command took 22 hours to arrive and another 22 hours for a response to return. Using programming tools and techniques from a computing era almost unrecognizable to modern software engineers. For a machine that has been in interstellar space for more than a decade, it worked. There's something in that story that says something about the people who work on this mission. The Voyager team at the Jet Propulsion Laboratory is a small group, dedicated, technically extraordinary, and in many cases, deeply attached to a mission that predates them personally. Some team members were not yet born when Voyager 1 launched. They joined the team years or decades into the mission and have had to learn the spacecraft from documentation rather than from experience. The original engineering team is largely gone, retired. Many no longer with us. The knowledge of how the spacecraft works, the specific quirks and characteristics that have developed over decades, the lessons learned through years of anomaly investigations, all of that has had to be carefully preserved and transferred. This is a different kind of challenge from building the spacecraft in the first place. Building requires creativity and engineering skill. Preserving requires discipline and documentation and a culture of knowledge transfer. The Voyager team has maintained that culture across nearly 5 decades. They've kept the documentation updated. They've ensured that new engineers learn from those with more experience. They've treated the institutional knowledge of the mission as something precious, because it is. When the 2023 anomaly hit, the team had access to computer memory maps from the 1970s, to assembly language code written before most modern programming languages existed, to hardware documentation in formats no longer commonly used. They had to work with all of it. They had to understand a computer architecture that is radically different from modern processors, and they made it work. That is a form of technical excellence that doesn't get celebrated the way discoveries do. But it is essential. Without it, Voyager 1 would have gone silent months before it did. The engineering on the ground has been as important as the engineering that went into space. The cosmic ray environment in interstellar space is something that needed to be understood before Voyager 1 got there. And what the spacecraft has found has both confirmed some predictions and forced revisions to others. Inside the heliosphere, the solar wind provides some degree of protection against galactic cosmic rays. The outward flow of solar particles creates a form of shielding. High-energy particles trying to enter the solar system from outside have to fight against that outward current, and many of them are deflected or slowed. This effect is called solar modulation. It means the intensity of cosmic rays inside the heliosphere is lower than what you'd find in the undisturbed interstellar medium. As Voyager 1 moved outward, the cosmic ray instruments showed the intensity of galactic cosmic rays increasing, as the modulation effect decreased with distance from the Sun. Then, when the spacecraft crossed the heliopause, the cosmic ray intensity jumped sharply again. Outside the heliosphere, In genuine interstellar space, there is no solar modulation. The cosmic rays are at their full galactic intensity. Energetic particles from across the galaxy, accelerated by supernova shockwaves and other violent phenomena, stream freely through the local interstellar medium. Voyager 1 is exposed to all of them. For electronics, cosmic rays pose a specific threat called single-event upsets. A high-energy particle passing through a memory chip can flip a stored bit, changing a 0 to a 1 or a 1 to a 0. If that bit is part of critical software or data, the effect can range from minor to catastrophic. Voyager 1's computers have accumulated cosmic ray hits over nearly 5 decades. The software has been designed with protections against single-event upsets, with error detection and correction capabilities. But these protections are not unlimited. After decades of exposure, the cumulative radiation damage is real. It contributes to the increasing fragility of the spacecraft. It is part of why each anomaly is taken more seriously now than similar anomalies earlier in the mission would have been. There is less margin left. Each recovery uses up some of that margin. The spacecraft is operating in territory where it was never designed to be, for durations it was never designed to sustain, and in a radiation environment it was designed to handle, but not indefinitely. That it continues to function is a tribute to the original design. That it requires increasingly careful management is an acknowledgement of reality. Before Voyager 1, our understanding of the interstellar medium was based entirely on remote observations. Astronomers could study the light from distant stars as it passed through the interstellar medium and analyze how the medium absorbed or scattered certain wavelengths. They could observe the emission lines of atoms in the interstellar medium, hydrogen being by far the most common. They could study radio waves from pulsars and measure how they were dispersed by electrons in the interstellar medium. From all of this, they built detailed models of what the interstellar medium looks like. But all of this was indirect. It was inference from observations made at a distance. What Voyager 1 provided was direct measurement. Instruments in the actual interstellar medium, sampling the actual particles, measuring the actual magnetic field, detecting the actual electron plasma. And direct measurement is almost always more informative than indirect inference. The first thing Voyager 1 revealed about the interstellar medium near our solar system is that it is not uniform. The density of electrons varies from place to place. The plasma wave instrument has detected these variations as changes in the frequency of plasma oscillations. Different regions have different electron densities. The medium has structure at scales smaller than the overall size of the heliosphere. The second thing it revealed is that the interstellar magnetic field near the heliopause is oriented differently from what theoretical models had predicted. Pre-Voyager models had suggested the galactic magnetic field in our local region of space should be oriented in a particular direction, based on observations of stellar polarization and other indirect measurements. When Voyager 1 crossed the heliopause, scientists expected the magnetic field to rotate, swinging around to line up with the galactic field beyond the Sun's influence. Instead, the magnetometer found the field pointing in almost the same direction as the field inside the heliosphere. It did not rotate the way the models said it should. This was a genuine surprise. The models had to change. The third major revelation concerns the structure of the heliosheath and the heliospheric boundary region. Theoretical models had predicted a relatively smooth, gradual transition from heliospheric to interstellar conditions. What the spacecraft found was a more turbulent, dynamic boundary than expected. There were fluctuations in particle densities. There were magnetic reconnection events, places where magnetic field lines of opposite polarity came together and snapped, releasing energy. There were structures and features that the models hadn't predicted. This complexity has direct implications for our understanding of how the heliosphere shields the inner solar system from the galactic environment, and how that shielding might change as the solar system moves through different regions of the galaxy over millions of years. Every time Voyager 1 tells us something we didn't expect, the models improve. Our picture of the interstellar medium, of the heliosphere, of the structure of the region around our solar system, is more accurate today because a machine the size of a small car flew into the places our models were describing and checked. That is science working exactly as it should. The magnetic field measurements from Voyager 1 deserve particular attention because they revealed something fundamental about the large-scale structure of our local region of the galaxy. Inside the heliosphere, the magnetic field is dominated by the Sun's field. The Sun has a powerful magnetic field that extends outward with the solar wind, carried along by the stream of charged particles. This interplanetary magnetic field spirals outward from the Sun like water from a spinning sprinkler, following a pattern described mathematically as the Parker spiral, named after the astrophysicist Eugene Parker, who predicted its shape in the 1950s. As Voyager 1 moved through the heliosheath, the magnetometer tracked how the field changed. Then, at the heliopause, the field structure changed abruptly. On the interstellar side, the magnetic field comes from the broader galaxy. It's not generated by our Sun. It's part of the diffuse magnetic field that threads through the Milky Way, generated by moving charged particles across vast regions of the galaxy over vast spans of time. The direction and strength of that field near the heliopause was measurable for the first time, and it connects to a larger question about the structure of the local bubble, the region of relatively low density, high-temperature gas that our solar system has been moving through for millions of years. The local bubble is thought to be the remnant of ancient supernova explosions that cleared out the surrounding interstellar medium. We live inside this bubble of hot, thin gas, moving through it. The magnetic field Voyager, one measured at the heliopause, is part of the field threading through the local bubble. Understanding it helps us understand the structure of the region of the galaxy we currently occupy. And that understanding matters for models of how cosmic rays propagate through our local environment, how the Sun interacts with its surroundings, and how the heliosphere itself will evolve as the solar system moves into different regions of the interstellar medium over millions of years. The trajectory of Voyager 1 through the outer solar system was not random. After the Saturn encounter in November of 1980, the spacecraft was directed onto a path that carried it above the plane of the solar system at an angle. Most of the planets orbit in roughly the same flat plane. Voyager 1 was sent at an angle to that plane, heading in the direction of the constellation Ophiuchus when projected onto the sky. This trajectory was chosen in part because of the Saturn flyby geometry required to visit Titan closely. Getting to Titan with the right flyby conditions meant the spacecraft would exit the Saturn encounter on a trajectory that swung it northward out of the ecliptic plane. The consequence is that Voyager 1 is now sampling a specific region of the heliosphere and interstellar medium, not the region in the direction toward which the solar system is moving through the galaxy, which is called the nose of the heliosphere, not the region directly behind, called the tail, but a region roughly perpendicular to the direction of the solar system's motion. Voyager 2, traveling in the general direction of the constellation Piscis Austrinus, is sampling a different region of the heliosphere boundary. Together, the two Voyager spacecraft are providing two sampling points of a structure that extends hundreds of billions of miles in every direction. Two data points are not enough to fully characterize such a vast structure, but they are dramatically better than zero. And the comparison between the Voyager 1 and Voyager 2 measurements taken from different directions relative to the heliosphere's structure has already provided insights into how the heliosphere is shaped by the relative motion of the solar system through the interstellar medium. The heliosphere is not a perfect sphere. It is elongated in some directions and compressed in others by the pressure of the surrounding interstellar medium and by the solar system's motion. Voyager data has helped constrain the shape of this elongation. Models of the heliosphere have been revised based on what the two spacecraft have found. The heliosphere that existed in textbooks before Voyager was a theoretical construct. The heliosphere that exists in textbooks now is informed by direct measurement. The pale blue dot photograph is perhaps the most famous image ever produced by a spacecraft, and the circumstances of its creation are worth knowing in detail. Carl Sagan had lobbied for the photograph for years. The idea was straightforward. Turn Voyager 1's cameras back toward the inner solar system, one final time before the imaging system was switched off to save power, and take a portrait of the solar system as seen from the outside. NASA was initially reluctant. The scientific value of the images would be limited. The inner planets are small when seen from several billion miles away. But Sagan argued that the value was not scientific in the conventional sense. It was philosophical. It was historical. Showing Earth as a tiny, fragile point of light suspended in the darkness of space would convey something about humanity's situation that no written description could fully communicate. NASA eventually agreed. The commands were sent. Voyager 1, about 3.7 billion miles from Earth, when the images were taken in February of 1990, turned its camera back toward the Sun. In the resulting image, Earth appears as a pale blue dot, less than a single pixel across, suspended in a beam of scattered sunlight that had reflected off the camera optics. The dot is so small and so faint that without the annotation indicating where it is, most people looking at the image would not notice it. That is the point. All of human history, all of human achievement and suffering and beauty and violence. Every person who has ever lived, every invention ever made, every story ever told, every child ever born. All of it contained in a barely visible mote of light. Sagan's accompanying text became one of the most widely read passages in all of science writing. The core of his message was that the photograph provides perspective. That from space, the things we consider enormously important look different when the planet on which they occur is barely visible. The photograph was taken by a machine running on nuclear decay, transmitted across nearly 4 billion miles on 22 watts of power, processed by computers in California, and became a document that has changed how millions of people think about their place in the universe. The imaging system was switched off afterward. The cameras would never take another photograph. But the pale blue dot was taken, and it will be remembered long after the spacecraft that took it has fallen silent. The gyroscopes on Voyager 1 are another element of the spacecraft that has required careful management. Gyroscopes maintain a reference orientation. They spin rapidly, and the angular momentum of a spinning gyroscope resists changes in orientation. If the spacecraft rotates slightly, the gyroscope senses the rotation, and the control system fires thrusters to correct it. For much of the mission, this was part of how Voyager 1 kept its antenna pointed at Earth as both the spacecraft and Earth moved through space. The gyroscopes on Voyager 1 had mechanical components: spinning elements, bearings, lubricants. In space, lubrication is a challenge. The lubricants used in space applications are specialized, designed to work across a wide temperature range and in a vacuum. But even the best lubricants degrade over time. For most of the mission, the gyroscopes were used only in special situations, to rotate the spacecraft for magnetic field calibration and for occasional maneuvers, rather than running continuously. By 2017, after 4 decades, gyro operations on Voyager 1 were brought to an end entirely. The reasoning was straightforward. The gyroscopes consumed power that was becoming increasingly scarce, and the spacecraft could hold its orientation without them, relying instead on its view of the Sun and a single bright star. This is the Celestial Reference System, and it is remarkably elegant. A sensor watches the Sun. A second sensor, the star tracker, locks onto the star Canopus. By keeping both of those reference points fixed in its field of view, the spacecraft knows exactly how it is oriented and fires its thrusters to correct any drift. No spinning gyroscope required. This kind of adaptive management is characteristic of how the Voyager mission has operated for decades. Every decision is a trade-off. Every choice to save power has a cost in redundancy or capability. Every choice to maintain a backup system has a cost in power. The mission continues because the team has been extraordinarily good at making these trade-offs in ways that maximize what the spacecraft can still do. The attitude control thrusters have their own operational history that illustrates how the mission has evolved. The thrusters are small rocket engines that burn hydrazine to produce tiny amounts of thrust. Their job is attitude control, keeping the spacecraft oriented correctly so that the antenna points at Earth. Over nearly 5 decades of operation, the main thrusters have been used far more often than originally planned. The spacecraft has been in operation much longer than its design life. More firings mean more hydrazine consumed. The hydrazine supply is finite. There is no refueling option. When it runs out, attitude control ends. To extend the propellant supply, mission controllers periodically switch to backup thrusters, which have been fired less often and have accumulated less wear. This distributes the propellant use across multiple thruster assemblies rather than exhausting a single set. In 2017, engineers fired a set of backup trajectory correction maneuver thrusters that had not been used since 1980, 37 years earlier. The worry was that they might not respond correctly after sitting dormant for nearly 4 decades in the extreme conditions of deep space. They fired perfectly. Another example of the original design, over-engineering, paying dividends. Then, in 2024, with some thruster lines clogging up from decades of use, engineers swapped to a less clogged set of thrusters that had been sitting idle for years. Again, they worked. The hydrazine propellant itself is expected to last well into the 2040s. It is not the propellant that will end the mission first. It is the power. As the RTG output keeps declining, attitude control and communication become harder to sustain together, and sometime in the early 2030s, there will likely no longer be enough power to keep the spacecraft talking. After that, attitude control becomes increasingly uncertain. The spacecraft may begin to drift. The antenna may wander off Earth. The communication link, which has been maintained for nearly 5 decades, will finally break. The end of the mission is defined by the intersection of multiple declining resources: power, propellant, functional electronics, working software. All of these are declining simultaneously. The mission ends when the combination of these declines makes continued operation impossible. Current projections suggest that moment arrives sometime in the late 2020s to early 2030s. The gold-plated records aboard each Voyager spacecraft are something most people have heard of, but few have thought deeply about. Each record is a 12-inch gold-plated copper disc, similar in format to the phonograph records that were a dominant audio medium in the 1970s. The information encoded on the record was selected by a committee chaired by Carl Sagan. The committee spent months deciding what to include. They included sounds, wind, rain, thunder, waves, birds, whales, laughter, a heartbeat. They included music from many cultures and many eras, from a Pygmy girl's initiation song to a Bach prelude, from a Georgian choral piece to Azerbaijani bagpipes to Louis Armstrong to Chuck Berry's Johnny B. Good. They included spoken greetings in 55 human languages and one greeting from humpback whales. They included images, encoded as audio signals that could be converted back into pictures by a sufficiently capable civilization with the instructions provided. There was a message from the then Secretary General of the United Nations, Kurt Waldheim. There was a message from United States President Jimmy Carter. There was a diagram using the positions of known pulsars that could, in principle, allow anyone who found the spacecraft to locate Earth's position in the galaxy. The record is encased in an aluminum jacket with instructions for playing it engraved on the surface. The jacket is gold-plated to resist corrosion. In the vacuum of interstellar space, protected from ultraviolet radiation by the spacecraft body, shielded from chemical corrosion by the near-perfect vacuum, the record is expected to remain physically intact for billions of years. The information on it will remain readable, in principle, for as long as any civilization capable of reading it exists and knows to look. There's a deep oddity in the record. It was made by a species that, at the time of making it, had not yet set foot on another planet, that had sent instruments to other worlds, but never humans. That was still very much confined to a single planet, orbiting an ordinary star in one arm of an ordinary spiral galaxy. And those people chose to send a record of themselves out into the interstellar medium, in a spacecraft that would drift for billions of years as a gesture toward whatever might be out there. Not because they expected a response. Not because they had any evidence that anyone would ever find it, but because the gesture itself seemed worth making, because the act of reaching outward, of saying we are here, we existed, this is what we were, seemed meaningful, even in the absence of any reason to believe it would reach anyone. That's a strange and very human thing to do, and Voyager 1 is carrying that gesture right now, through the dark, at 38,000 miles per hour. There is a broader question worth sitting with. Why does it matter that Voyager 1 is still functioning? The spacecraft is old. Its instruments are decades behind the state of the art. Modern spacecraft, launched today, would carry far more capable sensors. The data Voyager 1 sends back is limited in quantity by its slow transmission rate and limited by the capabilities of its aging instruments. The data rate is about 160 bits per second. Not a typo. 160 bits per second, from 16 billion miles away. A modern internet connection operates at millions of bits per second. Voyager is transmitting at the speed of an early 1960s modem. And yet the science community cares deeply. The answer is that Voyager 1 is in a place that no other instrument is. The data it collects cannot be replicated by any other asset currently in operation. We have no other spacecraft in interstellar space. We have no other in situ measurements of the interstellar medium, the heliopause region, or the cosmic ray environment beyond the heliosphere. Everything else we know about these regions comes from remote observations, from models, from theoretical calculations. Voyager 1's measurements, however limited in bandwidth and however old the instruments that make them, are unique. They are primary sources. They are ground truth. And ground truth for a region as important as the boundary between our solar system and the interstellar medium is irreplaceable. Scientists are still actively publishing research based on Voyager 1 data. Papers about the structure of the heliospheric boundary. Papers about the cosmic ray environment in the local interstellar medium. Papers about the magnetic field direction and intensity beyond the heliopause. Papers that revise our models of how the heliosphere interacts with the galaxy. None of this would be possible without the spacecraft. Every year that Voyager 1 continues to operate adds more data to the scientific record. Every year it falls silent is a data gap that can never be filled by any other means available to us. This is why the team at the Jet Propulsion Laboratory fights so hard for every additional month of operation. Every diagnostic performed, every anomaly resolved, every difficult power management decision made well, extends the period during which we have a direct connection to a region of space that no human-made object has ever reached. That value is real, even if it's harder to quantify than, say, the images from a space telescope. There's a perspective on Voyager 1 that astronomy textbooks rarely articulate clearly. We are, right now, in the only window of human history during which the Voyager mission exists as an active scientific endeavor. Voyager 1, launched in 1977. It will go silent in the early 2030s, give or take. That is a window of roughly 55 years. In the context of human civilization, 55 years is not very long. In the context of the universe's 13.8 billion year history, it is essentially nothing. The window during which humans can talk to Voyager 1, send it commands, receive its data, study its measurements, and actively learn from its presence in the interstellar medium is almost closed. In a few years, the signal will be gone. The spacecraft will still exist. It will be more distant, more silent, moving through the dark. But the conversation will be over. The people alive today are the people who live inside that window. The people who have the opportunity, if they choose to take it, to pay attention to what this machine is doing and what it is telling us. What it tells us about where our solar system ends and where the galaxy begins. What it tells us about the environment our solar system moves through. What it tells us about the cosmic ray flux, the magnetic field, the electron plasma of our local corner of the Milky Way. All of that is available now, and only now. After the signal stops, we will have the data already collected. But we won't get more. Not from Voyager 1. Not from anywhere like it, because there is nothing like it. The spacecraft launched most recently, with the potential to eventually reach interstellar space, is New Horizons, which flew past Pluto in 2015. New Horizons is currently in the outer heliosphere. It won't reach the heliopause for decades. We are watching the end of one chapter and waiting a very long time for the next one to begin. The question of what comes after Voyager, in terms of our ambitions for interstellar exploration, is genuinely open and genuinely uncertain. Several mission concepts have been proposed for dedicated interstellar precursor missions. The Interstellar Probe concept, developed at Johns Hopkins Applied Physics Laboratory, proposes a spacecraft that would reach more than 1,000 astronomical units from the Sun within 50 years, using advanced propulsion and modern instrument technology. 1,000 astronomical units would place it more than 8 times further than Voyager 1's current position. Modern instruments would return far higher data rates. It would be able to study the interstellar medium with a much more capable scientific payload. But as of the mid-2020s, no such mission has been approved and funded. The costs are substantial. The timescales are long. The scientific community has to compete for limited budget resources against other high-priority space science missions. The discussion continues. The advocacy continues. But the mission remains unflown. In the meantime, Voyager 1 remains the only instrument in interstellar space. The only direct source of in situ measurements from beyond the heliosphere, the only connection humanity has to the actual medium between the stars. That connection is precious precisely because of how hard it will be to replace. The trajectory of Voyager 1 after it goes silent is worth thinking about. The spacecraft will continue to move. Momentum in space is conserved. There is no air resistance to slow it down. There is no significant gravitational force from nearby objects to change its path. The gravitational influence of the Sun decreases with distance, and Voyager 1 is now so far from the Sun that the Sun's gravity has very little influence on its trajectory. For all practical purposes, Voyager 1 is on a straight-line path through interstellar space. It will move at approximately 38,000 miles per hour, essentially forever. Not quite forever, because eventually the gravitational field of nearby stars will gradually alter its trajectory over tens of thousands of years. But, for any human-relevant timescale, it will keep going in essentially the same direction. In about 40,000 years, the trajectory calculation shows that Voyager 1 will pass within roughly a light-year and a half of a star called Gliese 445. This is a faint red dwarf star in the constellation Camelopardalis, currently about 17 light-years from Earth. Voyager 1 won't enter the Gliese 445 star system. It won't be captured into orbit. It will just pass in the general vicinity and keep going. After that, no specific stellar encounter is predicted for hundreds of thousands of additional years. The spacecraft will drift through the galaxy, moving through the thin interstellar medium, passing through regions of slightly higher or lower gas density, but never encountering anything solid, never stopping, never being captured. The gold-plated copper record aboard the spacecraft will outlast the electronics by billions of years. In the vacuum of interstellar space, protected from chemical corrosion by the near-perfect vacuum and by the gold plating, the record is expected to be physically intact for billions of years. The information it carries, the sounds of Earth, the greetings in 55 languages, the music, the images encoded in the grooves, will remain retrievable, in principle, long after everything that built it is gone. That is a strange thing to contemplate. The craft itself will likely be recognizable as an artifact, as something made rather than something natural, for as long as the universe has stars. There is no natural process in interstellar space that would quickly destroy it. They could not have known that nearly 50 years later, their spacecraft would still be transmitting, carrying its instruments, carrying the antenna that used to point at Earth. Long after Earth is gone, long after the sun has expanded into a red giant and consumed the inner planets, long after the Milky Way has merged with the Andromeda galaxy, Voyager 1 will still be moving, somewhere in the resulting elliptical galaxy, still carrying its message to no one, or possibly to someone. We cannot know which. The people who built Voyager 1 could not have known it would become what it became. They built it to study Jupiter and Saturn. They hoped it would work well. They designed it carefully and conservatively, with more margin than the nominal mission required. But they could not have known in 1977 that they were building the first human artifact to enter interstellar space. They could not have known that nearly 50 years later, their spacecraft would still be transmitting. They could not have known that a new generation of engineers would be rewriting assembly code from their era to fix a corrupted chip across 16 billion miles. They couldn't have known that a photograph their spacecraft took of Earth in 1990 would become one of the most reproduced and quoted images in all of human history. They could not have known that the data their instruments collected would still be the subject of active scientific research nearly half a century after launch. They were building the best spacecraft they could with the tools and knowledge they had. And somehow, what they built exceeded every reasonable expectation by a margin that is hard to overstate. The engineers who will watch Voyager 1 go silent in the coming years will be watching something end that has been running since before they were born. For some of them, Voyager 1 has been a constant in their professional lives. A machine they've worried about and cared for and argued over in technical meetings. A source of unique, irreplaceable data. A connection to a part of the universe no other instrument can reach. When the signal finally stops, it won't be a failure. It will be the end of a mission that lasted 50 or more years beyond its design life. A machine that gave us everything it had, and then some. There is a human element to the Voyager mission that tends to get overlooked in the engineering discussion. The scientists who designed the instruments. The engineers who built the systems. The people who have spent careers monitoring a machine they will never see again, analyzing data that comes from a place no human being can go. Some of them have worked on the mission for decades. They've watched the power budget shrink year by year. They've made the hard calls about which instruments to switch off. They've held their breath during anomalies like the 2023 computer failure, waiting for data to come back across 40+ hours of round-trip light time, not knowing whether the fix they sent would work. And they've celebrated when the data came back clean, when the garbled signal sorted itself out, when the old machine, improbably, started working again. There's something quietly extraordinary about that. Dedicating years of your professional life to a machine that you cannot touch, cannot see, cannot reach. Knowing that everything you do is separated from the results by more than 20 hours of silence. Knowing that one day the signal will get weaker and weaker and eventually stop. Knowing that when it does, there will be no recovery. The mission ends when the power ends, and the power ends when the plutonium ends. And that is a fact as fixed as the laws of physics themselves. And doing it anyway. Caring about it anyway. Bringing the full weight of your expertise to bear on keeping an old machine alive across incomprehensible distances. Because the data it sends back is still unique and valuable and irreplaceable. That is its own kind of achievement. not inscribed in technical papers, not celebrated in the same way as the engineering breakthroughs, but real. Voyager 1 was designed in an era when the tools for designing spacecraft were slide rules and mainframe computers. The software was written in assembly language. The project management happened on paper. There was no internet to share files and coordinate across distances. There were no computer-aided design tools in the modern sense. The thermal models, the structural calculations, the orbital mechanics, all of it was done by hand, or with early mainframe computing resources that would seem laughably limited today. And yet, the spacecraft works. After nearly 5 decades in one of the most hostile environments the universe offers, after traveling further than any human-made object has ever traveled, after being operated by generations of engineers using documentation from before most of them were born, after surviving a computer failure that required remote firmware surgery across billions of miles of empty space, it still worked. There's something about that which resists easy framing. You could call it a triumph of human ingenuity. You could call it a testament to what's possible when the best engineers in the world are given a clear mission and enough time. You could call it luck, because there is certainly an element of that. Voyager 1 could have been struck by a particle too large to survive. The RTGs could have failed in some unpredicted way. A software error could have sent it into a tumble that permanently misaligned the antenna. Any number of things that didn't happen could have happened, but they didn't. And the spacecraft is out there right now, moving at 38,000 miles per hour through the space between stars. Still cold enough to be at risk. Still warm enough to function. Still talking. What does it mean that something we built is out there, right now, in the actual space between the stars? Not in orbit around Earth. Not on the way to a planet. In interstellar space. The same space that separates our solar system from every other star. The space that we once assumed could only be described theoretically, never directly measured. It means we crossed a boundary that had been crossed by no one and nothing from Earth before. It means we took a step, however small, beyond the reach of our own sun. And we did it not with a heroic crewed mission, not with a civilization-spanning engineering project. We did it with a machine the size of a small car, powered by the same physics that turns one element into another in the nuclei of atoms, carrying a message in a bottle in case anyone ever finds it. That's strange to sit with. The spacecraft is not romantic in its appearance. It's a structure of struts and equipment boxes, with a large dish on one side and a boom extending to carry the magnetometer away from the electronic interference of the body. It's not sleek. It's not beautiful in any conventional sense. But it's out there, in the dark, between the stars, still functioning, still talking, still measuring the faint hum of the plasma around it, still pointing its antenna home. And it will probably still be there, drifting in silence, when everything that built it is long gone. The interstellar medium that Voyager 1 is now sampling is not the empty void of science fiction. Nothing in the universe is completely empty. The interstellar medium between stars contains gas, mostly hydrogen and helium, at an average density of about 1 atom per cubic centimeter. That's extraordinarily thin by any earthly standard. The best vacuum chambers humans have built still contain around 10 million molecules per cubic centimeter. By our standards, the interstellar medium is essentially nothing. But it's not nothing. It has structure. It has magnetic fields. It has charged particles, mostly high-energy cosmic rays, accelerated by supernovae and other violent events elsewhere in the galaxy. It has dust grains, silicate, and carbon compounds, nanometers to micrometers in size, drifting on journeys so long they barely count as motion. The region of the galaxy Voyager 1 is currently passing through is called the local interstellar cloud, sometimes called the local fluff. It's a region of slightly denser, warmer gas that has been filling the space in our corner of the Milky Way. The local fluff itself sits inside a larger structure called the local bubble, a cavity about 1,000 light-years across, carved out of the interstellar medium by supernova explosions that occurred within the last 10 or 20 million years. The bubble's walls are shells of denser gas swept up by those ancient shock waves. Voyager 1 is still deep inside the local fluff. It will remain inside it for the foreseeable future. The boundaries of these structures are far beyond what any spacecraft we've ever built could reach in a human lifetime. What Voyager 1's plasma wave instrument has actually detected in interstellar space is the density of electrons in the medium. Shortly after crossing the heliopause, the instrument detected oscillations in the local plasma, essentially a hum of interstellar space. These oscillations allowed scientists to measure the electron density directly for the first time. The finding was slightly unexpected. The plasma density just outside the heliopause was higher than some models had predicted, which is not a contradiction of our understanding. It just means our models needed refinement. That's how science is supposed to work. You measure something. The model is wrong in some detail. You update the model. Voyager 1 has been updating models for nearly 50 years. There is something worth understanding about what Voyager 1 actually looks like as a physical object. It is not sleek. It was never meant to be aerodynamic, since there is no air between the stars. The central structure, called the bus, is a 10-sided aluminum framework, roughly 1.5 feet tall and about 6 feet across. Inside that frame sit the computers, the electronics, the fuel tanks, and most of the scientific instruments. The whole structure is wrapped in layers of multi-layer insulation blankets. Attached to the bus on a long boom is the high-gain antenna, the parabolic dish about 12 feet across. This is the face Voyager shows to the universe. Everything you've ever received from Voyager 1, every data packet, every measurement, every signal, came through that dish. It is pointed at Earth. It has been pointed at Earth for almost 50 years, making tiny adjustments as the geometry between Voyager and our planet slowly shifts. A magnetometer boom, about 43 feet long, extends from the spacecraft, designed to keep the magnetic sensors far from the spacecraft's own magnetic fields. On the main bus, you'd also find the cosmic ray instrument, the low-energy charged particle detector, the plasma wave system. And then there are the RTGs, 3 barrel-shaped cylinders arranged on 2 booms extending from the spacecraft. They look almost like an afterthought. They are anything but. Bolted to the outside of the bus and extended on booms for heat management, they have been generating the power and warmth that keep everything else alive for nearly half a century. The whole spacecraft, without propellant, weighs about 1,600 pounds, less than a small car. With propellant at launch, it was heavier, but the weight that matters once you're in space is the dry mass, the structure, the instruments, the computers, the RTGs. 1,600 pounds of human ingenuity hurtling through the dark between the stars at 38,000 miles per hour. Still talking. The power decline of the RTGs has been carefully tracked since launch, and the numbers tell a story about engineering at its most deliberate. At launch in 1977, the RTGs produced about 470 watts of electrical power. Each year, the output drops by a predictable amount as the plutonium-238 decays and the thermocouples degrade. By the mid-1990s, the output had dropped to around 335 watts. By the mid-2010s, it was around 250 watts. By the mid-2020s, it's somewhere around 200 watts. The decline curve is smooth and mathematically predictable. The radioactive decay follows an exponential curve set by physics. The thermocouple degradation adds another slower decline on top of that. Every year, the mission team recalculates the power budget. Every year, something new has to come off. Voyager 1's plasma science instrument stopped working back in 1980 and was eventually switched off in 2007 to save power. The planetary radio astronomy instrument and several others were powered down over the years as the budget tightened. The cosmic ray subsystem was switched off in early 2025, and the low-energy charged particle instrument followed in 2026. Today, only two science instruments are still running, the magnetometer and the plasma wave science instrument. These are the instruments that matter in interstellar space. They are the ones sampling the actual medium that Voyager 1 is flying through. As long as they can be kept running, and as long as there is enough power to transmit their data home, the mission has scientific value. The engineering challenge, every year, is to keep enough power available for those core instruments and the communication system simultaneously. When the power drops below that threshold, the mission ends. Not dramatically. Not catastrophically. Just quietly. The numbers will no longer add up, and the last remaining instruments will have to be switched off one by one. The transmitter will be the last thing running. And then, the transmitter too will fall silent. The fact that Voyager 1 has been in continuous operation for nearly 50 years raises a question that rarely gets asked directly. What is it actually like for the spacecraft to be out there? Not for the people watching it, but for the machine itself, in the most physical sense. The answer is mostly darkness and silence. Voyager 1 is moving through a medium so thin that it registers only through sensitive instruments. The light from the sun, at this distance, is roughly 10,000 times fainter than it appears from Earth. The sun is just a bright star. Not the dominant source of illumination it is from Earth, or from the inner solar system. From Voyager 1's location, the sky contains the same stars visible from Earth, but arranged the same way. Because the spacecraft has not yet traveled far enough to noticeably shift the apparent positions of even nearby stars. The nearest star in the direction Voyager is traveling is not particularly close. In about 40,000 years, the spacecraft will pass within a light-year and a half of Gliese 445, but right now there is nothing nearby. Just the very thin gas and magnetic field of the local interstellar cloud. The temperature of those gas particles, the individual atoms, is actually fairly high, around 6,000 to 10,000 degrees Kelvin. But remember that temperature is about the kinetic energy of individual particles. At the density of interstellar space, there are so few particles that even very energetic ones would transfer almost no heat to a spacecraft. The spacecraft doesn't care what temperature the interstellar gas is at. What matters is the radiation environment, the cosmic microwave background at 2.7 Kelvin, and the internal heat from the RTGs. The cosmic microwave background is the dominant thermal flaw. The RTGs are the dominant heat source. The insulation is the mediator between them. And the spacecraft interior, inside those insulating blankets, sits at a temperature warm enough to run electronics. Not comfortable by human standards, but survivable for the machines. The Voyager mission also forced a maturation in how NASA thinks about long-duration spacecraft operations. Before Voyager, most missions were planned in detail from launch to end. The mission profile was set. The instruments were defined. The data products were specified. The operations team executed the plan. Voyager broke that model almost immediately. As the spacecraft kept working beyond its primary mission, the team had to invent new ways of operating a spacecraft for which no long-term plan had been made. They developed new software tools for managing the power budget. They created new protocols for commanding a spacecraft across communication delays that kept growing. They built new expertise in the hardware and software of a system that no longer had any manufacturer support because the companies that built some of the components had long since changed or ceased to exist. They became, of necessity, experts in obsolete technology. Not because it was interesting as a historical exercise, but because that obsolete technology was the only technology available to keep a unique mission alive. The institutional knowledge that has accumulated at JPL over 5 decades of Voyager operations has no equivalent anywhere in the world. Nobody else has kept a spacecraft operational for this long. Nobody else has operated across this distance. Nobody else has had to diagnose and repair a computer from tens of billions of miles away with a 45-hour communication round trip. What JPL learned from Voyager has shaped how every subsequent deep space mission has been designed and operated. The redundancy philosophy, the power management approach, the careful thermal design, the institutional commitment to documentation and knowledge transfer. All of these practices, now standard in spacecraft design, were either invented or refined through the Voyager experience. The mission is not just a scientific achievement. It is an institutional achievement. A demonstration of what it takes for a human organization to sustain a technical endeavor across 5 decades and multiple generations of engineers. One of the quieter marvels of the Voyager mission is that the spacecraft has been able to navigate autonomously for essentially its entire operational life. Voyager 1 doesn't have a GPS system. There is no external reference frame to tell it where it is or which way it's pointing. Everything it needs to know about its orientation comes from onboard sensors. The star tracker that locks onto a known star, the sun sensor that tracks the direction of the sun, and the celestial mechanics calculations performed by the onboard computers. The star tracker has been particularly important. Voyager 1 uses 2 reference points in the sky. One is Canopus, the second brightest star in the night sky, a yellow-white supergiant about 300 light-years from Earth. The other is the Sun itself, used as a reference point for solar direction. By measuring the angles between these 2 reference sources and comparing them to expected values, the spacecraft can determine whether its orientation has drifted and fire the appropriate thrusters to correct it. This process has been happening continuously for nearly 50 years without any intervention from the ground. The celestial mechanics are handled by the attitude and articulation control system, one of the 3 onboard computers. Every few seconds, it checks the orientation, compares it to the target, and makes corrections if needed. 1,000 times a day, every day, for nearly 5 decades. The computer doing this runs on technology that would be laughably obsolete by any modern standard. But it has been running continuously for longer than most current software engineers have been alive. There is something almost meditative about the image of a spacecraft alone in interstellar space, quietly checking its orientation every few seconds against the stars, making tiny corrections, keeping its antenna pointed precisely at a planet hundreds of billions of miles away that it left nearly half a century ago. The machine is, in its way, a model of disciplined attention, doing the same thing, correctly, over and over, for as long as it physically can. The thermal margins that have kept the hydrazine liquid for decades are not the only place Voyager 1 has benefited from the original engineer's conservative approach. The thrusters that fired flawlessly in 2017, after sitting unused for 37 years, were designed with specifications that assumed a mission lifetime of 5 years. They were called on more than 4 decades later. The fact that they worked at all is a testament to the conservatism of the mechanical design. The lubricants throughout the spacecraft were chosen to last far longer than the design life. The bearing materials were selected for durability. The operating procedures were designed to minimize wear. None of this was because the designers expected the mission to last 50 years. It was because good engineering practice demands that you design things to be more durable than you expect to need, because reality has a way of surprising you. The people who built those systems in the early 1970s didn't know they were ensuring that a spacecraft would still be navigating in the 21st century. They were just being careful. The same can be said for the insulation. The same can be said for the computers. The same can be said for the thrusters that fired perfectly in 2017, after 37 years of dormancy. Every one of these systems benefited from engineers who built more robustly than the immediate requirement demanded. Good engineering is not about meeting the specification. Good engineering is about understanding that the specification might be wrong, or that circumstances might change, or that the machine might be needed for far longer than anyone currently plans, and then building accordingly. Voyager 1 is the most durable argument for that philosophy that has ever been launched into space. There is one more dimension to this story that deserves mention before we come to the end. Voyager 1 did not just reveal things about the outer reaches of our solar system. It changed how scientists think about the relationship between a star and its surroundings. Before Voyager, the heliosphere was largely a theoretical concept. We knew the sun produced a solar wind. We knew that solar wind had to stop somewhere, where it encountered the interstellar medium. We had estimates for where that stopping point might be, and those estimates turned out to be in the right general range, which is reassuring for the models. But knowing approximately where the boundary is and actually measuring what happens there are very different things. The heliosheath, the turbulent region between the termination shock and the heliopause, turned out to be more complex and more scientifically rich than anyone expected. The plasma there is hot and compressed. The magnetic field is tangled and dynamic. Energetic neutral atoms, produced when energetic charged particles exchange charge with neutral interstellar gas, stream through the heliosheath in patterns that encode information about both the solar wind and the surrounding interstellar medium. NASA's IBEX spacecraft, launched in 2008, detected these energetic neutral atoms remotely from Earth orbit and produced the first maps of the heliospheric boundary. But IBEX was observing from a distance. What Voyager 1 provided was the view from the inside. The two perspectives together, remote sensing and in situ measurement, have given scientists a far more complete picture of the heliospheric boundary than either could have provided alone. This is how science often works best. Multiple instruments, multiple techniques, multiple perspectives, all bearing on the same question. The answer that emerges is more reliable and more detailed than anything a single measurement could provide. Voyager 1 has been one node in that network of knowledge for decades. When it finally falls silent, that node goes dark. The ibex view will remain. Future missions will add their perspectives. But the direct in situ view from inside the interstellar medium, that is something that Voyager 1 uniquely provides, and losing it will leave a gap that will not be easily filled. It is not dramatic. It is not the end of a chapter in science. It is the quieter loss of a data source that has been reliable and unique and irreplaceable, going silent simply because the atoms that have been keeping it warm for 50 years are running out of energy to give. Physics, doing what physics does. Indifferent, as always, to what we would prefer. Tonight, we started with a simple question. Why hasn't Voyager 1 frozen in deep space? The complete answer, now that you have all the pieces, is this. The vacuum of space eliminates conduction and convection as mechanisms of heat transfer. The only way heat moves is through radiation. Radiation is slow and self-limiting. Voyager 1 carries RTGs that have been generating heat continuously since 1977 through the radioactive decay of plutonium-238. That heat is trapped by multi-layer insulation blankets designed conservatively, with more protection than the minimum required. The result is a spacecraft interior that has remained warm enough to operate for nearly 5 decades in an environment where the background temperature is within 5 degrees of absolute zero. The temperature of space is irrelevant to a spacecraft that generates its own heat and keeps it inside. The question was never whether space was cold. The question was always whether the spacecraft could maintain thermal equilibrium above its operating minimums. The answer, engineered into Voyager 1 before it ever launched, has been yes. Every year, the RTG power drops a little more. Every year, the thermal margins get a little tighter. The mission team has been methodically shutting down heaters and instruments to stay within the power budget. Eventually, probably sometime in the late 2020s or early 2030s, the power will drop below the minimum needed to run any instruments at all. Voyager 1 will go quiet. Not because it froze. Not because anything broke catastrophically. Not because it hit anything or got lost or was consumed by the void. Simply because the physics that has been keeping it warm for half a century will finally lose the race against the cold. The last signal will arrive at one of the deep space network antennas. Engineers will see the carrier frequency drop below the detection threshold. They'll wait to make sure it's not a temporary anomaly. It won't come back. The spacecraft will continue outward in silence, still carrying its record, still intact, still recognizably the machine that left Earth in September of 1977. Just dark. There are people alive today who have spent their entire professional careers working on this mission. For them, that silence will not be an engineering anomaly. It will be the end of something. The people who keep Voyager 1 alive are not doing it because the science return still justifies the budget, though it does. They are doing it because there is a spacecraft out there that is still alive, still talking, and as long as it is, someone should be listening. When you go outside tonight, somewhere in the sky above you, roughly in the direction of the constellation Ophiuchus, a small machine is moving through the dark between the stars. powered by atoms, guided by equations, still warm, still transmitting, still there, and still, after all this time, talking to us. Good night.